Thanks very much, Yoram, and thanks for having us here for a few days. I'm also going to give a talk in economics tomorrow with more neuroscience in it about stock price bubbles, and then more talks in computer science on Thursday, so we're here for a few days. And also I'm going on sabbatical next year to Oxford, and so actually being in the college atmosphere is exactly getting me in the mood, but I don't think it will be as gorgeous as here. Okay. I'm going to talk about strategic thinking. Actually, I won't say too much about brains, just for time permitting, but if we may have time later or tomorrow, as I said, I'm going to talk about brains and stock price, experimental stock price bubbles. So first of all, how many people know a fair amount of game theory, like took a course? Okay, perfect. So you're going to be a little bored at parts of this, and others I'm going to try to catch you up on what are really the essential ideas in game theory without too much notation. Game theory, as it's often worked on, is extremely mathematical, but a lot of the intuitions are really simple and are captured by simple games, some of which we'll see today. I'll show you 4 data sets. Okay, so strategic thinking, as I'll refer to it, is reasoning about what other organisms, could be genes actually, or nations or companies. I'll usually default and talk about humans or kin of humans. Reasoning about what other organisms will believe, value, and choose, and then taking action. And so a standard approach to this is game theory, which is a collection of mathematical modeling devices. I'll say a little bit more in a minute. And once the game is set up, it's a mathematical object, sort of a description of elements in the world. The empirical and analytical question is, what are players going to do? And so I'll distinguish between 2 fundamentally different approaches. There's a few more interesting approaches I won't have time to talk about. If you were studying the mathematics of this, you could take a whole year course or study for years. One is called equilibrium analysis, and one is called cognitive hierarchy. And this is a book that's now 10 years old, but is not getting obsolete too quickly, which is a mixed blessing, of course. Okay, so an equilibrium is a mathematical definition of a state of affairs in which players, sorry, I should give you the background. What are the elements of a game? Players, they have information, maybe about what other players are likely to do, or about states of nature, like whether it's raining or how many troops are in Crimea. The players are going to have an order of moves. Sometimes the moves are actually actions. Sometimes they're imposed, by rules or in an experiment. The players, given their information and their order of moves, take actions. The set of all those actions determine outcomes, and the outcomes are things that occur in the world. It could be wars, they could be fitness in biology, it could be profits from companies. And we assume the players have numerical utility over those outcomes. So they can boil outcomes down into things they can rank, I like this more than this, or maybe even give a cardinal numerical measure. So that set of mathematical constructs is called a game. And so now the question is, what do the players do, given all that structure? So equilibrium analysis says players figure out what others are likely to do and guess correctly and optimize. So the strategies that all the players pick match up with the beliefs the players have about the strategies that all the players pick. So it uses a recursive kind of fixed point logic. It's very elegant. This is really the big idea for which John Nash shared the Nobel Prize. But it's always left an open question of, how does this equilibrium come about? Is it because they learn? Is it because they all went to some kind of a common school and so they know how one another thinks, like a bunch of chess masters? Is it something like biological evolution that leads to an equilibrium? And so an alternative view, you might call it pre-equilibrium game theory and non-equilibrium, is that not all players correctly guess what others do. And instead, one way to model this that's proved to be pretty fruitful, this is the core idea in most of my talk, is what's called a cognitive hierarchy, or sometimes called a level K approach. The idea is that some players aren't thinking strategically at all. They use something non-strategic that's kind of a heuristic. They might pick a lucky number, or they did what other people told them to do, or if they're picking a price, they might pick the center, they might pick the highest price. They're going to do something quick and easy. A one-step player thinks they're playing zero-step players. So they're not thinking strategically, because they're not really attributing any kind of purposive intention to the zero-step player, but they're not making dumb mistakes. Two-step players think they're playing 1 step and 0. 3-step players think they're playing 2, 1, 0, and so forth. And so as you move up this hierarchy, 2 things happen. One is that there's a lot more cognition required in a combinatorial sense, if we think it's deliberate cognition rather than, say, something adapted. And the higher order players basically have a better view of what's really going on. They have a more and more correct view of how other people like you to play, which means they'll earn more money. Okay. We've developed this in a bunch of papers starting about 10 years ago, and many other people have also. Okay. let me quickly say what it is we would like a good model to do, because computer scientists often have a somewhat different view than social scientists, and economists have a somewhat special view. We're trying to basically do a little bit of everything. That is, fundamentally, these models are very empirical. We would like them to have interesting theoretical properties and some transparency, but that hasn't been my contribution. Other people are making good progress on some elements of understanding the deep theoretical foundations. Mostly we would like to fit data, and not just one game at a time. Like, we don't want a separate explanation for each game. We'd like to be able to have a principle, and you can email me a game, and I can say the prediction of the theory is this, and we can see if that's correct. So far, people have looked at about 150 different games in lab settings, and about 7 field data sets. I'll show you 2 of those today, and I think a few more on the way of field data. Second, we would sort of like there to be some predictability, maybe in the form of a behavioral parameter or 2. Today I'll talk about a single parameter model. The only way to do better is a 0 parameter model. And often the single parameter is going to kind of buy you something. The one we focus on is called tau. It's the average number of steps of thinking. So if tau is, say, 2, that means the average person is doing 2 steps of thinking. So there's some distribution, 0, 1, 2, 3, 4, and the average is 2. Empirically, we find that numbers like 1 to 3 fit a lot of data sets pretty well. We should be able to say when equilibrium is likely to be wrong and right. I'll show you some examples. And this is my sort of somewhat recent project. We would also, if we think of these algorithmic steps as things that people are actually computing, we should be able to see kind of process data, as psychologists call it, or maybe neuroscientific data. We should be able to see parts of the brain that are active when people are doing more reasoning. Maybe they have slower response times. Maybe we can see where their eye looks on a computer screen, or they're looking at certain kinds of information. So most game theorists don't collect these types of data, but we do. And we think this provides a lot of constraint on the theories. Okay, I'm going to talk about quickly a couple of relatively simple games, lab and field. I'll say just a teeny bit about eye tracking. fMRI, you'll have to ask me later or read some papers. I'll say a little bit about movies. It's a field application. And a final thing that's fun. Okay, a very simple game to warm up. This is a game that's been studied a lot of times, so I'll show you just a couple of snippets of data, but there's maybe 30 or 40 papers. It replicates quite nicely up to sort of a behavioral shifts, which makes sense depending on something like the player's sophistication. People pick a number from 0 to 100. The closest to 2/3 of the average of all those numbers wins. That's it. So I can describe the rules of the game very easily, right? You're going to simultaneously pick a number. The computer or some process will compute the average, and whoever's closest to 2/3 of the average wins a fixed prize, right? Whether you're above or below doesn't matter. It's just closest in absolute distance. So it's an easy game to describe in rules, right? Think about what you might do. There are a lot of data on this. What many people do is to say, I'm really not sure what people are going to do. They could pick any old number, so I'll pick 33. That's 2/3 of the average of random, right? That's not a bad choice, but it's not an equilibrium choice, right? Because if you believed everyone would pick 33, you should pick 22. But if you believed everyone would pick 22, you should pick 2/3 of 22. And in fact, remember that by definition, equilibrium, sometimes called Nash equilibrium, because it's in these games we're going to use the original concept due to Nash, which has been refined and tinkered with in a lot of interesting ways. We're just going to use the plain off-the-shelf Nash. In the Nash equilibrium, everybody's beliefs have to match with what everybody else does, right? So if everyone picks 22, thinking everyone's going to pick 33, their beliefs that people are picking 33 are wrong. People are picking 22, not 33. And so the only point at which beliefs match up with choice is the solution to the equation x star equals 2/3 of x star, right? Choices are a best response to people choosing those choices, and that's 0. But notice this shows you kind of the extremity of Nash equilibrium. That's part of why people studied this game originally in the lab, right? It assumes this iterative process of adjusting to what you think people you're thinking doing, doesn't stop until you reach a resting point. And it's an extreme number. And it's also bad advice, right? So if you pick 0, you're not going to win. You might get the right answer on a final exam, what's the Nash equilibrium, but if you're playing this game, say, for money, like we do in the lab, you're not going to win. What's going to win? This is a lab sample from National University of Singapore engineering students. They're pretty sharp analytically. The data are in magenta or purple. What you can see is that most of the data are sort of between 50 and 0. There's a big spike of 33. Those are people doing one step of reasoning, like one step in our mathematical model. Okay? There's a few people picking really high numbers. These are kind of instructive. It turns out that These numbers are either 80 or 88. My wife is Chinese and Tech is from Singapore, and he claims those are lucky numbers in Chinese. Not so lucky here. Right? In fact, those are actually dominated numbers. You'd be much better off picking lower numbers than that, because that's just too high. And a few people pick low numbers, like close to 0, but in a way they're being too smart for their own good, like too clever by half, as we'll say in Oxford, in the sense that that's the correct answer to the question, what if people are using near equilibrium reasoning, but it's not the best answer to the question, what is a typical amount of thinking people are doing in the experiment that you should try to match. And this is a nice study that uses about 9,000 observations from 3 write-in contests where people wrote in to 2 magazines and 1 newspaper. And as you can see, so these are self-selected people. The distribution, you basically don't see too many high numbers, but other than that, you see the distribution slide down. There's a 33 and 22 and a bunch of people picking 1. The average of that is 23. 2/3 of that is about 15. So if you pick 15, you'd kind of be on the right track in that data set. The winning number here is a little higher. Okay, this is Reinhard Zelten. So in 1998, this is a quote that just kind of reminds you of how cognitive hierarchy thinking is different than equilibrium. He said, the natural way of looking at game situations is not based on circular concepts. By circular, he means the best strategy is the thing which is the best response to people choosing the best strategy. Instead, it's a step-by-step reasoning procedure. So that's what kind of inspired this structure. So this is just a little bit more math recapping what I've said. To run this machine, we need a distribution of steps f of k, where k is the number of steps. How many people do 0 steps? How many do 1? How many do 2? We need to say what the 0-step players do. You need to be as principled as possible. We don't want to look at the game and say, well, if you think the zeros are doing this, it'll fit the data. We prefer to have a kind of a single idea of what the starting process point is for the process. That's something we're still working on, by the way. And then the k-step players think everyone is below them, so they're all kind of overconfident. They all think they're smarter than everybody else. And an alternative is that a 3-step player thinks everyone is 2 steps. That's a slightly different variant within this family. So what is f of k? There's a bunch of things you can do. If you assume this proportionality condition, then that implies an f of k function, which is Poisson. Poisson is a really nice function here because it has a single parameter, which is the mean and the variance. And also the Poisson distribution, the percentage of people, for example, if tau is 1.5, a Poisson distribution with a mean of 1.5, has a fair amount of 0 levels players, mostly level 1s, that's the mode, and then 2, 3, 4s drop off very fast, which we think is probably realistic because of the kind of biological constraints of having to do a lot of reasoning. Okay, this is just this is designed to overwhelm you. This is a partial list from a couple of years ago of applications of these theories. So a lot of people have been using this in different games. Okay, this is a game we ran across. Robert Ostling deserves the credit for this, who's from Sweden. So he emailed me and said, there's this lottery people have been playing in Sweden, and I can get all the data from it. And the way it works is that people pick a number, an integer, a whole number, from 1 to 99,999. That's because if you go to the lottery and buy this card, each number you fill out the numbers here, and the maximum is 99999. That's where the constraint comes from. So if for each number you fill out on this card you can pick up to 6 different numbers. You pay €1 and you can win a prize. And again, like the other game, the rules are simple. It doesn't mean their logic is simple, but the rules are simple. Pick a number from 1 to 100,000 minus 1. Right? Everyone's going to do this at the same time, we assume. So you don't get to peek and see what everybody else does in the theory. And the lowest number that's unique wins a fixed prize. That's it. So the rules are easy. You pick an integer in a certain range, lowest unique number wins. That's it. Now, the math is hard. In fact, if you try to solve for a Nash equilibrium, it's impossible computationally. Now, I should add, every time I've given this talk, impossible meaning we couldn't do it, which was me. I definitely couldn't do it. Eileen Chow, not so great. Joseph Wong's wife was a PhD in math from Taiwan, really brilliant person. She couldn't do it. Robert couldn't do it. Every time I gave this talk in a mixed audience, particularly with computer scientists, I'll do this on Thursday, I get some email from somebody saying, oh, I think I can solve this. I'll email you later. And apparently in computer science, later means infinity. Or we'd occasionally get an apologetic note, I'm still working on it, I'm still working on it, I'm almost there. Anyway, so now that isn't to say that it couldn't be solved, but there's something about the combinatorics that make it extremely difficult. However, if the number of players each time is not fixed, if the number of players is fixed, that's the case that's hard to solve for a large number of players. In Sweden, the average number is 53,000. That's hard to solve. If the number is not the same every time, coincidentally, if the distribution of the number of players also has a Poisson distribution, thank you, Roger Myerson, Nobel laureate, now at Chicago. Myerson proved a bunch of theorems about how if you have games with large numbers of players that are variable, like voting, right, where there's a distribution of how many people will vote, it's not just a fixed number. It turns out that if that distribution is Poisson, it introduces a lot of beautiful, just magical tractability. So if we assume the number of players varies day to day to day, which as it turns out it does, it doesn't look exactly like a Poisson, but this is our only chance, then you can actually solve the equilibrium, and it's a mixed equilibrium. That means that nobody does the same thing every time. They're going to choose a probability of each number. So the distribution is going to be a profile of picking 1 and 3 and 517 and so on. And the percentage of people picking number k plus 1, that's p of k plus 1, the percentage picking k plus 1, and the percentage picking p of k is related by a series of these equations. So you write down these equations and solve. And it turns out you get a very interesting prediction. One prediction you get is that of all of these numbers up to 100,000, you should only pick the lowest 5,000 numbers, according to this theory. 95% of the numbers should never be picked. That's a pretty bold prediction, right? The theory rules out 95% of all the numbers. It also means they basically designed the auction wrong, because when they designed it, they didn't compute this. And so they held these wasted space on the cards, basically. In theory. What happens? So here's what happens. Sorry, I apologize. This is a little hard to see. Anyway, this is the full distribution. What you see is the data is a bunch of spikes. Let me step out a bit. And so what you see is, in fact, indeed, not many people pick really high numbers. There's a few spikes here which are probably round numbers, or there's some number that has significance in Sweden or something like that. They're not winning numbers. They're level 0 numbers. But way too many people picking 1. So the 1 is like the sound of the naive player. Lowest unique number. I'm going to pick 1. No one else will think of that. Right? There's 53,000 other people. None of them are going to think of picking 1. Right? And so you get way too many low numbers. That's a kind of an index that they need to peg. But if you hone in on just the lowest 10,000 numbers, throw out the top 90%, and you blow up that 10, this is 10,000, that's 100,000, look carefully, right? The theory is not too bad. It basically says you should pick smaller numbers more often, which you do. But people definitely overshoot. There's too many numbers that are a bit high, like 9,000, and then there's not enough numbers in here. And by the way, the theory has an amazing structure, right? The theory basically says the numbers from 0 to 5,513 should be chosen about equally often, and then there's a very sharp drop-off to epsilon. 1 is should be most common, 2 is a little less common, 3 is a little less common, until 5,513. And so this partly is meant to show you the boldness of Nash equilibrium game theory, right? You take these rules, integer up to 100,000, 53,000 players, Poisson distributed, lowest unique wins. You build this machine, and you get this crazy prediction. Flat numbers up to 5,513. Like, who knew? 5,513, right? So game theory does some amazing things, but it doesn't fit the data great. This is the data from the first 7 days that people play this lottery. So, of course, we think they're probably still equilibrating and learning and talking to their friends. So, it's not surprising that Nash equilibrium doesn't fit too well here. The question is the cognitive hierarchy model going to do better? So it turns out if you fit a cognitive hierarchy model, you're going to use a tau parameter. That's the average number of steps of thinking. In addition, we need basically a softmax response because there's so many choices. If you don't put in softmax, the model just fits horribly. If you do that, you get a pretty nice fit. Now, again, that's 2 parameters. If you're an economist in the audience, you might say, well, with 2 parameters, you can fit anything. We have 2.5 million observations, so you can easily leave 1 out or leave 1 million out. And there's no question that these models are not overfitting. And happily, we get a nice tau number of 1.8, which is pretty close to what we see in a lot of experiments. And by the way, remember, this is not an experiment. This is the field data. This is it's sort of like an experiment that somebody did in Sweden, in the sense that it's nicely structured, and theory makes a really clear prediction. And we then went back and replicated in the lab. Here, we see something in the field. We go back to the lab and try to take it apart and understand it. These are students from UCLA. We had 26 of them playing numbers from 1 to 99, so we kind of shrank the game down. And the prediction now is that the lowest number should be chosen in almost a triangular distribution that goes down from 1 to 13, and nobody should pick more than 13. Again, that's a bold prediction. That means the numbers 15 to 99 should never get picked. And the theory fits great. It fits really great. But there's a little bit of a gap here, sort of like in these data. Too many low numbers, very low numbers. Too many high numbers. That's just because there's more than epsilon. And then there's kind of a gap in the middle. There's not quite enough people picking in the middle part of the distribution. If you play this 7 weeks in Sweden, by the 7th week, the theory looks really good. If you kind of kernel smooth this, it would look quite nice. So this is simultaneously a game in which 7 weeks of learning and watching on the news who won and talking to each other brings the number of low numbers way down. People picking 1 and 5 and 10 realize that typically the lowest unique winning number is about 2,000. So they see in the news, 2,000 won the lottery. Oh, maybe 1 was too low. And they adjust upward. They adjust upward using a kind of very typical adaptive learning dynamics. At least that's our best guess. And the result of that process, it's still very spiky, and there's too many low numbers, but at least they're starting to fill in this gap. And you see basically lots of choices up to 4,000 instead of 5,000. So again, this is the game theory prediction. The Nash equilibrium prediction is a 0 parameter, very bold prediction that nobody had even computed until our paper. Okay, eye track. I'm just going to say something very quick about this. This cognitive hierarchy approach lends itself very naturally to eye tracking, because the level 0 players don't have to look at anything. So if you see somebody who's just, looking at the rows and saying, well, I'm going to pick the top, or I like middle, I like 18 because I'm 18 years old. They shouldn't look at much payoff information, and that we can then classify them as, kind of naive, non-strategic players. The level 1 players, if you think about the logic, they think others are random. They just need to look at their own payoffs, because they're not trying to figure out what other players would do by using the other players' payoffs. They're not treating the others as doing anything deliberate and purposive. So if you see players who just look at their own payoffs and not the other guy, we're going to classify them as level 1. And so we've done this in several studies. I probably will talk about some on Thursday in computer science. But the main thing you see is this is an eye tracking graph showing where they're looking. This is the row players' payoffs, and this is the column players' payoffs. They're separated into 2 separate matrices. And mostly they look at their own payoffs, about 50% more than the others. So that's consistent with this level 1 limited reasoning. Okay, making okay progress. Who saw this movie? It's kind of pretty old now. It was terrible, correct? Empirically speaking. So this is a study, this is now a field application. As we're going to now use this level K reasoning to try to understand a particular interesting practice in the movie business, and an effect it has on box office gross. When we do this kind of study, this is not my expertise, but Alex Brown did a terrific job. You kind of appreciate the comfort of the lab, because you need to make a lot of assumptions about exactly what's going on in the movie business, and they're not going to map into the math quite so well. But I think that the example is instructive, and we get kind of a nice result. So it turns out that from 2000 to 2006 in the U.S., for movies that are shown on to widescreen audiences, that's more than 600 screens, so we're excluding kind of art movies and smaller movies, just big release movies. All the movies were shown to critics in order for the critics to be able to write something in the Friday newspaper, except for 7% of them. Those were not shown to critics in time to get reviews in the paper on purpose. So those are called cold opened. In the last few years, that number went up a lot. Now, of course, there's a lot of changes in the movie business over this period of time, right? Lower box office gross, DVD rentals go up, the role of influential film critics at the New York Times or the Globe and Mail, gradually decreases because of the internet and blah, blah, blah. So, there's actually an historical pattern that's going on. If you were to look at this phenomenon from now, I don't even, it makes sense to study it. It's a very different type of business. And so the question is, why are they not showing these movies to critics? Okay. So there's an unraveling argument. You can look at the notation, but I'll try to kind of explain it visually. So here's the idea. This is a very influential argument due to Paul Milgram and Sandy Grossman that was made in the 1980s. And it went right to a policy debate about if there's a single dimension of quality, like calories, quality of movie, how durable a product is, like a battery, should the government force firms to disclose that, or should they expect firms to do it voluntarily? And the argument is that rational firms and rational consumers will lead to voluntary disclosure. Here's why. Suppose you have movies on a scale like 0 to 100. The people with the best movies will show those to critics. They'll want critics to say, wow, this is really above average. That means that a movie that's like a 45 gets lumped in with all the other movies. So somebody says, the RM says, wow, the Pluto Nash, I didn't read any reviews for that. It's probably just below average. Right? So he thinks, well, if it's a uniform distribution, it's probably like a 25. But that means that the 45s really need to disclose how good they are. So they want the critics to say, this is below average, but it's not really terrible. And then those movies will get voluntarily disclosed in the sense of allowing reviewers to talk about it. So then when those are disclosed, then the movies that are 25 to 0 don't get disclosed. And then the 25s are like, wow, we're getting lumped in with Ashton Kutcher. Oh, man, we don't want to be lumped in with Ashton Kutcher. We want critics to say, this is a pretty mediocre movie, but it's not the worst you'll see this year. Right? Like, that's a glowing review. That's the best we're going to do. And so the theory is that you'll have voluntary disclosure at the high end, and if consumers are adjusting their expectations to what non-disclosed, unreviewed movies mean, you'll gradually get all the movies being shown except for the very dregs. Okay. All right. Here's an example. Notice, and the way you can tell if the movies are cold open, very simple. If critics see the movie in advance, they usually send a draft of the review to the publicist, and they put it in these newspaper ads. Right? And so there's no quotes here. Right? And there's Captain Hagel and Ashton Kutcher. What more do you need to know? I was giving this talk once, and I said, has anyone seen this? The guy said, yeah, my wife, yeah, I saw it with my wife. I said, was that your ex-wife? He goes, yeah, it is my ex-wife, as a matter of fact. So we can even predict marriage and divorce in this model. This movie, by contrast, has a whole bunch of nice quotes about how great it is. That's because first of all, it's a smaller movie, so it doesn't quite fit our model. And it's a movie where they wanted the critics to say, this is really great. We're not going to spend a lot of money in advertising, but we want the critics to propel the movie. Right? And it has Colin Farrell in it. So my middle name is actually Farrell. And when I was coming back from England, there was somebody looking at my passport. So, Colin Farrell? Yeah, Colin Farrell. It's like, wait a minute. Like the actor. Like the actor. Yeah, pretty much. Yeah, we're mistaken a lot. Okay. This is a histogram that shows Metacritic ratings. This is an average of 30 critics' ratings put onto a uniform scale and then added up. It looks nice and Gaussian, doesn't it? Right? Nice and Gaussian. And this is the number of movies in different critic rating categories. So these are the really outstanding ones. These are the really terrible ones, as judged by critics. It turns out, by the way, if you do this with fan ratings from IMDb, not critics, they're very highly correlated. So across these movies, it's not the case that critics love certain movies that the fans hate. Even within like the horror movie genre, across a sample of horror movies, there are ones that the fans will think are better than average and the critics will think are better than average, and then there's others that everybody hates. Okay. And the red ones are cold openings. So you can see that if the movies are above average, actually very much like the rational theory predicts, they're always shown to critics. In this worst category, there's 50 movies that are 20 and below, half of them were not shown and half are shown. So the theory we're going to test is whether sophisticated moviegoers will kind of act as if they know this distribution. So if they see a red movie, there's no quotes. They think, oh, it's probably between 0 to 40. That's where most of the reds are, right? A naive moviegoer will say, gee, I don't know if that really tells us anything, whether the movie was reviewed or not. If I don't hear anything about it, it's probably average. So they're going to be fooled by the fact that the studios willingly don't show it to critics. And that's what we think that's what the studios are after, right? The studios want people to think, oh, I didn't hear anything about that movie. Instead of saying, oh, that's really a bad sign, because the best movies get reviewed, and if I don't hear anything about it, it means it's terrible. They want the moviegoers to think, ah, that doesn't really mean much. Okay, here's some quotes that kind of indicate that. Here's just a little bit of data. This is a little bit of fancy statistics. Actually, not fancy statistics. We're going to run a regression of box office against a whole bunch of control variables. That's things like the number of screens, production budget, star power measured in certain ways that movie fans work on. And we're going to leave out the quality variable so you can see how influential quality is. That's the critic measure of quality, or fans. Again, the results are the same. And we're going to leave out the cold opening dummy variable. So if fans are fooled by these cold openings, there'll be an extra high return to the cold open movies because they think the quality is higher than it really is. And they're going to kind of turn out to see the movie and they're going to be disappointed. That's something else we can see in the data, but I don't have time to show you. Okay. So this is a regression of the residuals from that equation against Metacritic rating. The blues are the ones that are shown to critics. And so basically there is a substantial correlation. Ratings do influence box office, although not perfectly, right? There are certainly lots of movies with great critic ratings people don't go see, and then movies that critics hate, which have huge box office. And the red ones are the cold openings. So you see two things in this graph. They're at the bottom of the Metacritic rating pile. I showed you that before, right? And if you run a regression line for the cold openings separately from all the blues, the intercept is positive. That means conditional on everything else, including quality, because it's later assessed, critics will review it later after it's out, there's a bump in cold opening. It's about 15%. It's pretty substantial. And it's significant in a bunch of different time periods. And there's a lot more econometrics in our paper if you want to read about it. Okay. So I didn't show you any brain data. If I had, well, I did show you this. If I had it, it would look here. So what we've established so far is how this cognitive approach works. We started with a very simple lab game that was also done in newspapers. Then we went to the Swedish lottery. We also did that in the lab again. And then I showed you an example of a kind of field application of this type of model to explain an institutional practice and to be able to say something about consumer mistakes. On to the last part. Okay, Humans 1.0. This is work about a primatologist, as you might be able to tell, but Tetsuro Matsuzawa is a very prominent one in Japan, and Chris Martin is the grad student working in Japan, an American who did most of the practical work here. Okay, so we're going to study how chimps and humans play simple competitive games. These are games kind of like hide and seek, right, or what's called matching pennies. They're going to choose left or right on a computer screen at the same time. One animal gets rewarded if they both choose left or they both choose right. They want to match. That's like the seeker. They want to find the location, right? The other animal wins if they mismatch. Left and right, right and left. They're like the hider. They want the seeker to go to a different location, okay? Okay. All right. And what motivated us was, this is an idea of Matsuzawa's. It hasn't been that well publicized, but I think it's extremely fascinating, is what he calls the cognitive trade-off hypothesis. First, the chimps are better than us at some things. If you don't believe me, go wrestle a chimp, who probably will kill you. They're very strong and very fast. When you see them fight, it's kind of like these kung fu movies where they have everything like artificially sped up. They're really fierce. Could it be that they're cognitively better in some ways too? I mean, this is a wild hypothesis. And so Matsuzawa said maybe. We know they're actually pretty good at a few things, like upside-down face perception, people aren't that good at. If you're seeing a face right set up versus upside, there's a big change in performance. They're pretty good at matching voice and face, and a few other things. And so we're going to see when they play these competitive games whether the chimps may actually be pretty good at that. And the theory is that as humans evolved language and became pro-social, the chimps are kind of left behind. They spend a lot more of their time engaging in status competition, like wrestling, playing tag, you know, things where one person wins and one loses to kind of move up the status chain. Like if you watch children play, they'll start playing tag and hide and seek, and then later they'll move to kind of group play, where they do things that are cooperative, like building stuff together. The chimps never make the transition. So we think that they may have kind of evolved capacity to randomize in the service of competition, i.e. status demonstration, quite well, and also the young chimps practice it a lot. They get a lot of practice in these games in their natural ecology. Okay, there's an upside down face. It's Donald Trump. Chimps and humans are also genetically quite close. Interestingly, zebras and horses are further apart genetically than chimps and humans. And not only are they our closest cousins genetically, we're their closest cousins. So they're closer to us than they are to gorilla and bonobo and pongo, orangutan, despite the surface similarity in hairstyle. Okay, so a couple of films and then one or two slides and we'll be done. This is a spatial number memory hold task. 5 numbers come up on the screen, 5 digits, 200 milliseconds. They're replaced by squares. You have to press this, where the numbers were in ascending order, right? You have to press the squares corresponding to the lowest, next lowest. That's a mistake. That's a win. It means win. Means mistake. Okay? So humans get about 60% right. There's some controversy about what happens if you train them extensively, because the chimps are going to have many thousands of trials of training. Can the humans do as well? We actually don't know much about that. There's only been a couple of studies training humans, for weeks and weeks and weeks. And so we don't know if we can catch up. But as you can see, that highly trained young chimps, especially the young ones, are pretty good. They get apple cubes. So if he's right, he picks up an apple cube. Notice how effortless it is. Huh? What?
Explain to the chimps what they're supposed to do.
It's pure reinforcement learning. So first you have to train them that 1 is lower than 2. So you present 1 and 2 on the screen, and you reward them if they pick 1. So they're just learning by pure, it's called shaping, by tons of reinforcement, what ascending numbers look like, and doing this test. I mean, it takes many, many months. Okay, so what we're going to do is we're going to play 3 games with them that are these matching type games. We're going to press left or right. And we're going to change one parameter, which is x. So it turns out in these games, there's a unique mixed strategy equilibrium. That means there's a probability with which the different chimps, the matchers we're trying to match, and the mismatchers trying to mismatch, will choose left and right. And it has an amazing property. All the games basically have this structure. So the winner is going to get 1 apple cube as a reward, right? The matcher is going to win if they match left, left, or right, right. They get x or 1, x cubes or 1. The base game is where x equals 1. Then they should mix left and right 50% of the time. But if we change x, I mean, this is just going to sound ridiculous. It is ridiculous. If we change x, like we made x equal to 3, so now if the matcher matches on left, they get 3 apple cubes. That shouldn't change the probability of which choosing right at all. It should change the column player. Those of you who know some game theory will know this. The reason is that in equilibrium, if the matcher is always playing left, trying to get those 3 apple cubes, the column player will kind of figure that out and always move right. And so changing x will not change the predicted play of the matcher who benefits from x. It will change the predicted play of the other player, right? And this has been shown to not hold quite well in human data, quite a bit. So the two chimps are going to play in a room next to each other. I'll show you one more film. So they're both choosing left or right. After they choose, they see what the other person did. They get the feedback. Come on, come on, come on. Okay. So data. There's a bunch of things we're going to study. I'm just going to today focus on choice frequencies. How often do they choose left and right? There's a lot more we can say about learning and response times. It turns out the chimps are very, very fast at this, sort of like with fighting. And fortunately, we can graph this in a very nice, compact way, which is great if you're giving a talk and trying to finish. Okay? Every game is going to produce essentially the following data. For each subject, these chimp subjects play 200 trials in the morning, and the next day they switch roles. So they go matcher, mismatcher, matcher, mismatcher, and play 200 more. They play about 1,000 trials, and we're going to average them. In the papers, we do have a lot of sophisticated studies of learning and how that works, but I'm just going to show you the raw picture today. And so IE, for example, who's here, is a very famous chimp, actually, a 30-year-old female. This triangle is going to plot the percentage of time she chose right when she was matching and the percentage of time she chose right when she was mismatching. Okay? So we can just see, and the Nash equilibrium is 50-50. The matcher should play 50%, the mismatcher is 50%. This is a game with symmetric. It's when that x value from before equals 1. And so you can see that none of them are smack on 50-50, but they're kind of hovering right around it. And as it turns out, there's 6 chimps. which is a reasonable number for these type of behavioral study. They don't usually have very large sample sizes. If you average these, they're going to be really, really close to 50-50. But, that could mean that because they're just randomizing equally. They're not doing anything more sophisticated. Now we change X to 3. The prediction is that the Nash equilibrium should move up here. The matcher should not move, but the mismatcher should change. So the player who's getting more amplitude should not change on average. The other player should change. And that's sort of what happens, but they slide a bit over here. And this is when we change X to 4. We change it a little bit more. And now they move up. And again, no individual chimp is that close. Well, not none. 3 chimps are close to the Nash equilibrium and 3 or 4 apart. But if you average them, it's incredibly close, right? So here you can barely tell which symbol is which. The Nash equilibrium is a square. The other ones are triangles. Right on, right on. Slightly off. And here, it's just off in 1. The matchers choose about 40%. They should be choosing 50. So I claim that this is the best evidence of Nash mixing we've ever seen in any species. And it's better than most human data, which I know quite a bit about. At least I did 10 years ago. There may be a lot more studies I haven't kept up with. Here's some human data. So the humans also played one of those games. It's the game where X equals 4. And the humans move away from from 50-50 in the direction of Nash equilibrium, but not very strongly. And these are actually 2 different samples, one Japanese and one Africans who are playing for money for about a day's wages. So they're pretty highly motivated. Okay. There's some fancy math explaining why that works, but you saw the main part of it. So Arthur Robson will appreciate this. We think what's going on here is that this tells you that game theory may have a lot of value interpreted in what Ken Bidmore calls an evolutive view. That is, it explains what's likely to happen when animals are performing in sort of an ecology in which the payoffs are really relevant to them. And maybe they have preserved brain regions to keep track of competition and do pattern recognition. And they may have a lot of time as infants and toddlers, essentially the chimp equivalent toddlers, to practice. And this is a quote from Bidmore. So I'll end with this. Thanks.
Okay. I don't think I've given a talk with this many wires in many years, if ever. Anyway, thanks very much to the college and to the organizers for having me. It's also a great pleasure to speak with Colin, who was an inspiration and encourager in my sort of starting and continuing this line of research, which began maybe, 8 or so years ago. When I first started it, I wasn't sure if it was a one-off joke or if I was serious about it, and he convinced me to be serious about it, so here I am. So there's a number of different angles one can take in thinking about this research, or motivations. And in the interest of time and also to coordinate with Colin's talk better, I'm going to skip the prefix of motivations you see here and maybe return to it at end. I do think that the experiments I'm going to describe to you today point the way towards maybe an eventual theory about many modern phenomena like crowdsourcing and other forms of social computation, citizen science, peer production, and the like, of the kind that you might be familiar with, ESP game, Folded, Galaxy Zoo, basically using volunteer or paid labor online to conduct large-scale either behavioral experiments or to actually get some form of work done, as in the case of Folded. But an alternative view of the work I'm going to describe is much more basic and much more closely related to Colin's talk, which is you can really think about what I'm going to describe here as experiments in behavioral game theory with one major twist, which is that it's taking place in a network. So the experiments I'm going to describe to you in many ways are much, much messier than the ones that Colin described. But they're larger scale in one very particular sense, which is the number of subjects, and in particular the fact that there's some sort of network structure mediating the interaction between the subjects. And I hope that it doesn't need a lot of motivation why we want to study social and strategic interaction in networks these days, but if I have time at the end, I'll return to this connection to things like citizen science and social computation. But let me start by just describing in a somewhat dry way the type of experiments that we've been doing in my group at Penn starting in back around 2006. So these are human subject experiments that are kind of deliberately and militantly interdisciplinary. They're at the intersection of computer science, economics and game theory, sociology to some extent, and the emerging field that has unfortunately chosen to call itself network science, but it appears to be too late to do anything about it. In these experiments, we bring groups of human subjects into a laboratory environment in about 3 dozen subjects at a time, and everybody sits at a networked workstation. And in each experiment, a subject is controlling some very simple property of just a single vertex or node, which you might call their node, in an underlying network that none of the subjects are aware of. So this is the main design variable that as experimenters we're picking, which is what does the network structure that's mediating their interaction look like. The subjects know nothing about that structure in advance and can only glean whatever they can glean about it from interaction during the experiment. So the subjects only have local views of the activity, the state of their own, and the neighboring vertices or nodes in the network. Okay? And in the hallowed tradition of behavioral game theory, we're not paying subjects for mere participation. It's eat what you kill. So every subject has a real financial incentive to solve their piece of some collective global task or competitive game. I'll go through the variety of things we've tried before, but we're really paying for performance, okay, not for showing up. So let me give a simple and provocative example that kind of was the very first set of experiments we did and has a very strong computer science motivation to it, which is the problem of graph coloring. How many people have heard of the graph coloring problem before? Okay. So graph coloring is this famous problem in computer science, both for its applications in many hard combinatorial optimization problems like scheduling exams in a limited number of rooms, and also for its notorious computational intractability in a worst-case sense that's technical that I won't go into, but it's basically a hard problem for which there aren't really good known general-purpose algorithms. Okay? But you can also think of graph coloring as a very natural problem of social differentiation where you want to distinguish yourselves from the other people that you spend time with, let's say in your social network. So a stylized version of this problem of social differentiation would be everybody's given the same fixed vocabulary of colors, let's say red, blue, and green. And at each moment in the experiment, all you have to do is pick a color for your vertex. And at each moment in the experiment, you get to see the color of your own vertex and all of the neighboring vertex in the network, but not the colors of the vertices or players that aren't your immediate neighbors. Okay? And the payoffs for the experiment, let's say, are that you get paid some fixed amount, let's say a few dollars for an experiment that lasts a few minutes, if when time expires, you're a different color than all of your neighbors. So you want to distinguish yourself from your neighbors. When I was asked by the editor of the journal for a real-world example where this problem might actually arise, it took some thinking, but a good one is picking a cell phone ringtone from a fixed menu of provided ringtones. Let's say you have an iPhone, you have many people that you hang around with an iPhone, and you'd like to pick a ringtone which is different than the people you spend a lot of time with, so that when the canonical marimba tone goes off, we're not all reaching into our pockets to figure out whose phone is going off at the symphony. Okay? So the problem, like many of the examples that Colin gave, is very simple to state. It's very easy to motivate, but it's known that computationally, on very large, complex networks, there aren't really any good known algorithms for this problem. So one of the motivations here is, I'm not trying to refute complexity theory, as it's called in computer science, but one question is, whether human subjects in at least small or medium-sized populations can solve problems like these on reasonably complicated networks. Okay, so this is the kind of thing we've been doing. And what we've been doing over the years is, across many, many different experimental sessions, we've been deliberately varying a lot of stuff. It's a huge design space. But the two main design variables that we've been playing around with are the network structure. What does the topology, if you like, of the network look like? And what task are the subjects trying to solve, or what game are they playing? And especially, how do these two things interact, right? How does network structure influence outcome or behavior, both as predicted by theory, when there is a theory? I mean, certainly there's no theory predicting, or there wasn't at the time of these experiments, predicting how human subjects would behave in graph coloring experiments on complicated networks. But it's a perfectly reasonable question to ask. And we've also been varying the nature of the task. And we've been varying the task essentially for diversity. For instance, whether the game is a cooperative one or a competitive one, what the difficulty of the problem is according to centralized computational theories, et cetera, that I'm not going to detail. Okay? And so we're interested in questions like how does structure and task interact and influence performance and behavior. We're interested in individual and collective modeling, possibly for the purposes of prediction, although, as you'll see, we're very far from the sort of extent of prediction that you can do in the types of experiments that Colin discussed. And we're also interested in what computation and equilibrium theories have to say about these things. So for some of the games that I'll describe to you, either computer science or economics thinks it has something to say about which networks should be easier or harder, whether subjects should be able to do it at all, let's say in the case of graph coloring. And in some cases, it's albeit a minority, we have experiments where there's a fairly detailed equilibrium theory saying exactly how network structure should influence, let's say, who gets richer or who gets poorer in some sort of network trading game. And then you can go run an experiment and ask, is this actually what the wealths look like? Okay? Okay, like Colin, I have a slide meant to overwhelm you, or as I sometimes put it, you're mercifully not meant to read this slide. This is just showing you a list of all of the different experiments we've done to date, organized by the game or the task that the subjects were engaged in, which is the natural way, by the way, to organize the experiments. What takes a lot of training and overhead is to explain a new task like graph coloring to a group of 36 human subjects. Once they understand what graph coloring is, I just want to be a different color than all my neighbors, it's relatively easy to run them through a series of short, let's say, 2 to 5 minute experiments, each with a different network. Okay? If there's something to take away from this slide, it's the very shotgun nature of the experiments we've been doing. So if you just restrict your attention to the design variables of what the network structure looks like and what the task is, already, it's many, many more careers than I will ever have to even sparsely populate that design space. So we had to make an early decision about whether to kind of go very deep on one problem like graph coloring under a very specific type of topology or take a shotgun approach. Your answer is here. We took a shotgun approach. And today I'm only going to talk about the very simplest types of games that we did that actually don't have very strong equilibrium theories in the economic sense, but have fairly strong computational theories. So problems like graph coloring, which computer science says should be a hard problem, consensus, which computer science says should be a trivial problem, things like biased voting. I'm mainly going to talk about those three. I'm not going to talk about the others. Tomorrow in economics, I'll talk about networked trading. That'll be a more technical talk. And that's sort of the nicest set of experiments from the perspective of there being a very, very precise equilibrium theory that predicts equilibrium outcomes and wealths as a function of network structure, whatever the network might be. Okay? So if you're interested in that and want more technical detail and math, then come to Econ tomorrow. Okay. But let me just, what I want to do today is, I'm not going to really describe results in any detail, although I'll give you some hint at what results might even look like in this area and what some of the more provocative findings we've had are. But I first just want to start by giving you a sense of, what does it feel like to be a subject in these experiments, and what does the collective behavior look like at a macroscopic level from the experimenter's viewpoint. So if you were a subject in our very earliest coloring experiments, your screen interface would look something like this. You're seeing a fragment of a network over 36 vertices here, of which you're only seeing 4. One of them is you, which is always clearly marked in the middle. And then you're seeing these 3 other vertices that you have direct connections to. They are your network neighbors. We're also showing you a little bit of additional information here, which is the edges between your neighbors. So it's basically, you know who your friends are. You know which pairs of your friends are friends with each other, but that's all you know. Okay? In all of the experiments we've done, just to get some technical details away, the only communication allowed in the experiments is through the system itself. We erect physical partitions so that people can't easily see any workstation other than their own. When the subjects are students, the most expedient thing to do is to tell them to behave as if they're in a final exam. That sort of this says it all in a very short amount of time. And all of the games are asynchronous move. So in this game, you can click on any one of these buttons anytime you want, as many times as you want. It will instantaneously update your color on your monitor and also your color on the monitor of anybody that is your network neighbor. Okay? And then at the top, there's usually things like a progress bar telling you, an elapsed time telling you how much time is left in the experiments. We have to put some sort of upper limit on the time, otherwise we might give them one network to color and they're there for 3 hours and they fail to do it and nobody gets paid anything and we don't get any data and nobody's happy. So it does introduce a clipping bias in the data. But in general, we found, as I'll say in the punchline that I'll foreshadow at the end, people turn out to be quite good at everything we've thrown at them. So we've been able to sort of reduce that upper limit gradually over the years and get more data in, and then the subjects are happier because they're getting more payment as well. Okay? Okay, so this is the basic framework. And in the very first set of experiments we did, these were there were a series, and every one of these experiments, they're doing the same task like graph coloring, but we're in each experiment swapping in a different network topology. This shows you the actual 6 specific network structures over, in this case, we actually had 38 subjects this time, that we did in our original graph coloring experiments. You might wonder what hat we pulled these network structures out of. I won't go into detail on them, but generally, one category of network we use are networks that are drawn from generative models for social networks that are a topic of great study. So the pages of Science and Nature are littered over the last 10 to 15 years with articles both arguing empirically that large-scale social networks like the Facebook social graph have certain common structural properties that are very reliable if you blur your eyes appropriately. Many of you, even if you aren't familiar with this field, already know some about this. So this is the sort of, the apocryphal 6 degrees of separation, or the notion of connectors or hubs in social networks whose number of neighbors is not just large, but many, many orders of magnitude larger than the average. And then there's a theory side of this literature in which people sort of say, oh, hey, networks, large-scale social networks seem to have these 3 properties very, very commonly. Let's try to think of a simple generative model that generates a distribution over networks that would, in expectation, have all those properties simultaneously. So models like preferential attachment, for instance, are models which are deliberately designed to generate networks that will have a heavy-tailed degree distribution, small world networks which are, often very simple lattice-like structures like a simple one-dimensional lattice, also known as a cycle, with some random cross chords added. These are meant to generate networks in which both the diameter is small as you add more chords, but also have what's called a high clustering coefficient, meaning friends of friends are more likely to be friends than 2 people chosen at random from the background. So that's just a little bit of motivation. Sometimes we'll throw in something much more kind of handcrafted or engineered here just because we have some theory about what might happen in that network. So again, it's a very breadth-first approach to this particular design variable. Okay, now you might ask yourself, okay, so what I'm showing you are the 6 actual networks given to the subjects, and in each case I'm showing you an optimal coloring, right? So I'm showing you, you could tediously verify in each one of these cases that every pair of vertices that's connected by an edge has a different color on the 2 endpoints, okay? And so not only are these proper colorings, as it's called, but they're also optimal, meaning they use the fewest number of colors. So this is easy to see in the cycle, right? It's a cycle with an even number of vertices, so you can just go red, green, red, green, red, green, red, green, and everybody will be a different color. For these preferential attachment networks, this is a much harder problem. This is a network over 38 vertices that happens to be 4 colorable. And just so you get a sense of why this problem is challenging, right? There are vertices in this network which have neighbors, a number of neighbors that's in the teens, okay? So, at least behaviorally, it's quite likely that subjects playing those vertices will find all 4 of the available colors used by their neighbors, and their only choice will be which subset of neighbors to conflict with, meaning have the same color as, okay? So you might think about like, well, which of these would be easier for you to color if I gave you the network and colored pencils, and which would be harder, and which would be easier or harder for the subjects, and just to, you know, show you the kind of thing that actually happens experimentally. This is a home movie showing you the actual play. This is a movie showing the actual play of subjects trying to color a cycle. And these were our very first set of experiments, so they had a full 5 minutes to do it. I think just in the interest of time, this is sped up by maybe a factor of 2 or 3. But, you know, subjects, you know, this experiment starts, subjects pick red or green. You know, they enter at different times. They can do kind of whatever they want. And very quickly, we get down to a very small number of conflict edges, which are the ones that are meant to be easier to see. They're in black. So anywhere you see a black edge, it's an adjacent pair that has the same color. And even though, of course, this is an incredibly simple network, in fact, there's almost a mathematical certainty to what has to happen here. If there are two conflict edges, if they can propagate towards each other, then they kind of collide and can't destroy each other because the vertex in the middle can resolve the two conflicts. Okay? But remember, you have the luxury of seeing something here that none of the subjects did. All every subject knows is that they have two neighbors and that they're not those two neighbors aren't connected to each other. There's no sense of knowing that there's a cycle. There's not even a notion of clockwise or counterclockwise, and you don't know what everybody else sees. Okay? And so this is a case where after fully 5 minutes, the subjects failed to find a solution. There's still a small number of conflict edges, you know, here and there. There's one over here. There's one over here that might be about to get resolved if we'd let the experiment go a couple of minutes longer. And you can see that they kind of get it, even though they don't know everything they need to know. If I kind of scroll back and forth here, kind of just drag this back and forth a bit, you can see there's sort of local attempts to purposefully propagate conflicts one direction or the other, but because nobody has this bird's eye view, they never get around to finding a solution even after a full 5 minutes. Here's this nasty looking spaghetti network generated by preferential attachment, showing the same set of subjects trying to four-color this much more complicated network. You see this vertex 2 in the middle here, which has a very large number of neighbors. All of the available colors are used in this in their neighborhood. And you know, they make a change, and then suddenly there's a whole bunch of new conflict edges. You know, what needs to happen here is a little bit different. And this sort of gets at this idea of network structure kind of interacting with dynamics and outcome. What really needs to happen here is that the high degree vertices, they're usually going to be in this state of having conflict. And you know, one possible strategy for them is to make a choice and try to stick with it and hope that the conflicts can propagate out to the edge of the network where it can be resolved by, you know, these fixer vertices. So this is a 3-colorable network. So here's a degree 2 vertex in a 3-colorable network. They can resolve any conflict that arrives at them. Okay? And so this, in contrast, is something that was solved well under 5 minutes. And I would posit that if I'd given you these two networks, the cycle and preferential attachment, and 2 and 3 colored pencils, and asked, you know, explained coloring to you and asked you all to solve these problems, I'm pretty sure everybody would have solved the cycle by now, whereas I doubt anybody would have solved the preferential attachment network. Okay? Okay. Just to sort of show one more visualization of data, one of the things that's fun about these experiments is that they really give all kinds of creative opportunities for one's artistic side. So these Rothko-like drawings are actually visualizations of a problem which you can think of as complementary but in some sense opposite to coloring, which is the same thing, choose a color for your vertex, but now your goal is to be the same color as your neighbors rather than a different color. And so the maximum welfare solutions, if you like, where everybody's getting paid, are the ones where there's a single global color throughout the entire network, i.e. everybody's paying red. Okay? And what I'm showing you here are visualizations of collective play when the network basically looked like this network or something very close to it. So by this network or something very close to it, I mean either literally this network or this network with maybe a few of these edges erased and replaced with random edges between arbitrarily chosen pairs of vertices. This is a very common type of model, right? So you can think of this original network as a very stylized cartoon for a highly tribal culture, where you have complete interconnectivity between every pair within the members of a tribe of group 6, okay? But then every tribe has a leader which has a loose connectivity to adjoining leaders in this chain-like structure, okay? And I can sort of gradually erase that highly clustered tribal structure by just randomly going around and deciding to replace some fraction of the edges with random long-distance connections and create a parametric model where I have kind of a continuum between this highly clustered world, but where distances from one end to the other are relatively large, to something that looks like a completely random network where distances will be short, but sort of natural tribal or clustering structure. So, and I can generate anything in between by tuning this knob, okay? As Colin said, right, having a free parameter lets one do a lot of things. So think about this network or networks where there's only been a small amount of this erasure or rewiring, and where the goal is everybody is the same color as everybody else. Unlike graph coloring, there's not a natural number of colors to give here, right? In graph coloring, there's a minimum number of colors. This is like the famous 4-color theorem. There's a minimum number of colors for any graph required to find a solution. Here, right, so, and in general, the smaller that number is, all things being equal, kind of the harder the problem is because it's more constrained, right? I mean, if I have a graph of n vertices and I'm given n colors, then the structure doesn't matter. I can just give everybody a different color. Here, in general, more colors makes it harder because rather than being a hard kind of combinatorial optimization problem, it's a pure coordination problem here, right? So we arbitrarily chose 9 colors as, you know, sort of a number of colors that we thought we could render distinctly on the display and seemed challenging. And what these visualizations are showing you is elapsed time in the experiment is on the x-axis. Then for each player, there is a row. And the value of the row at the given elapsed time is just what color that player chose at that particular time. Okay? So one thing that's great about these visualizations is that in a single glance you see all kinds of interesting examples of both individual and collective behavior. Okay? So first of all, it's hard to see, but every one of these experiments starts off with kind of the full variety of colors being chosen, sort of all 9 colors being used in the first several seconds of the experiment. And then, as in this diagram, very quickly you get down to just a handful of colors, right? Oh, and by the way, because of this nice structure of the network, I'm of course choosing to arrange the rows here such that the first 6 rows correspond to this tribe of 6, the next 6 rows correspond to this tribe of 6, etc. Okay? So what you can see here is that very quickly on, the first tribe is settling on brown, then the next 2 are settling on yellow, then there's the next one that's brown, and then 2 that are red. So we quickly kind of prune the colors down to a small handful until about midway through the experiment, we're really down to just 2 colors on opposite sides of the network. Okay? But there are still these tribal leaders that are the only ones that are aware of the fact, right, that we haven't reached uniform consensus yet. In particular, they're not going to get paid yet, because they have 2 neighbors that are different colors. They can't, not all their neighbors are the same color. Okay? So there's some tribe leader out there where, that has both a red and a yellow neighbor, and they need to, in order to get any payment, they need to sort of convince their tribe to kind of go with one color or the other. Okay? Okay, so in terms of individual behavior, first of all, one of the things that's fascinating about these experiments is these are highly stylized experiments in which, admittedly, we are kind of taking away much of what it means to actually be a human being. For instance, language, but I guess this is common to much of game theory. But the first thing that people do in these experiments, no matter what the game is they try to reinvent language, right? So you see all kinds of acts of signaling, right? So, these signals are most likely somebody who's sitting in the middle of a brown clique that has neighbors in this yellow group over here and is trying to experiment around with getting their clique to change. You also see, kind of toggling back and forth between all of the colors in short succession for who knows what reason. You see apparently irrational behavior, like this cowboy here who, for almost the entire experiment, is playing a color that's not being selected anywhere else in the network. At the collective level, you can generally see that, right, we do get to this phenomenon of a small number of colors And in all of the 5 cases I'm showing you, and in almost all of the, I think in all but one of the experiments that we ran on consensus, it's hard to see here, but the end of the experiment, if the subjects ever reached unanimity to a color, we stopped the experiment and went on to the next one. And in all 5 of, in the first 4 of these, we're reaching unanimity, for instance, to yellow, right? So the picture ends here when this last individual changed from blue to yellow and the experiment ended. This is the only one that didn't end in unanimity after whatever it was, 2 minutes that we gave them. And just the dynamics here are fascinating, right? So we very quickly get to just 3 colors. About a third of the way through, brown is the majority, and there are these 2 holdout cliques. A short time after that, blue has taken over, and there's only this 1 holdout clique. A short while after that, they give it up and switch over to blue, but not just before they can create this little trickle of their original color, which propagates to the other side of the network and takes firm hold over there until a short while later, that's actually the majority color. And when the experiment ends here, it's about 50-50 between blue and green. Okay? And so again, this is, an anecdotal example of the interplay between network structure, in this case, this highly tribal structure and variance of it, and kind of the dynamics of play in a group of 40 subjects or so. Okay. Okay, so I'm not going to be very technical in describing results. I'm going to describe results at a very high level. You can go read source papers if you like, if you want, the gory details and statistical significance values and the like. But just to give some sample findings. First of all, and I'll quantify this a little bit at the end. We generally find very strong collective performance. So this is an informal statement that I'll make precise towards the end. But in general, whatever problems we've thrown at subjects, whatever network structures we've thrown at them, when we've reduced the amount of time they had to perform the task, etc., they generally tend to surprise us with how well they do. And I'll tell you how you can measure that despite the difference between the tasks and the networks. The answer is money, right? We're paying money here, and we know how much we could have paid them and how much they earn. Structure matters and may depend strongly on task. So, our papers are kind of filled with many examples of tasks and network structures where you could, in a reasonably quantifiable and certain way, say for this task, these types of network structures facilitate collective performance, and these types of network structures seem harmful to collective performance. And more importantly, there aren't universals there. It seemed, and maybe this isn't surprising, but if you know the network on literature science, which is kind of obsessed with topology and structure alone, divorced from dynamics, it's an important message that the same structural modification that you make to a family of networks that's helpful for one task might be harmful for another. So even within, and that's what this plot is showing here, I'll just summarize what it says in English. It basically shows that in this family of models where you start with this tribal structure and gradually do some erasure, the systematic replacement of tribal structure with long-distance connectivity is helpful to the consensus problem and harmful to the coloring problem. So even these 2 problems that, at least from a cognitive standpoint, are very similar. What could be easier? Before you were trying to be a different color than your neighbors, now you want to be the same color. You can even run these 2 tasks in the same session, and subjects can immediately make the switch. But the effects of this particular surgery or operation on network structure has the opposite effects on the difficulty of the problem. Okay? Other surprising, things is that sometimes more information can actually harm performance. So in our original experiments, we played around with how much information you had about the network structure, from only seeing your local neighborhood to seeing a little bit more to seeing the whole thing. And that systematically degraded performance, at least for the more complicated types of networks. For things like the cycle, it's incredibly helpful for everybody to see the global structure. But for things, because immediately people see what needs to happen, right? They can see, oh, here's a conflict, and I just need to propagate that over here to meet this other conflict. When you show them a preferential attachment network, showing them the entire network badly harms their performance collectively. And there's, unfortunately, like all these things, there's many theories for that. It could be information overload. But there were also many reports by the subjects that seeing the entire network made them more patient, made them appreciate that even though they didn't have any conflicts in their neighborhood, maybe there were conflicts elsewhere in the network, so sometimes they would change color when they didn't need to locally to help out, which maybe actually was harmful. So it's sort of food for thought that maybe there's, you know, a benefit in sort of shaping collective behavior to not give people more information, even if they can handle it, because it might cause them to adapt heuristics or strategies that are actually harmful to the collective, and maybe it's better if they just focus on their little piece. Let me describe, what time are we going to? Till 6:30? Is that? I can't remember. Huh? Okay. So let me describe one more set of experiments we did that was that's very much in this kind of just pick a color and you're trying to coordinate in some sense with your neighbors or with the rest of the network. But it has a very crucial strategic twist. And these experiments were sort of were done at around the time of and were loosely inspired by the very contentious Democratic primary between Obama and Hillary Clinton back in 2008. But the biased voting problem is cosmetically very similar to consensus, but with a crucial strategic difference. So you can either read the slide or you can just listen, which might be easier. So like consensus, the incentives are that you want to be the same color. Everybody wants to be the same color, but now there's only two choices, red and blue. Okay? And the payoffs work as follows. Now they're going to be collective, right? It's not just whether you're the same color as your neighbors. It's whether the whole network is the same color. So the incentives are if within the 2 minutes allotted, absolutely everybody in the network has chosen red at some point, or everybody has chosen blue, then everybody will be paid something. If that condition doesn't hold within 2 minutes, everybody gets paid nothing. So if 35 of us choose red and one of us chooses blue, we all get nothing. So the first order strategic effect is a strong incentive towards unanimity. If we don't reach unanimity, none of us get paid anything. Okay? But the crucial strategic twist is that in the same 2-minute experiment, different players will have opposite incentives. So I might get paid $1.50 if we reach unanimity to blue and only 50 cents if we reach red, and you might have the opposite incentives. So we all want to reach unanimity, but we care about which color and we disagree about which color we want to converge to. Okay? Okay. So this is, unlike the two experiments I described before, I've introduced here what an economist would call a type. Right? Before, everybody's utility functions were symmetric, be the same color, be a different color. Now they're be the same color but prefer red, or be the same color and prefer blue. And so this introduces yet another kind of design variable, which is not only are you picking network structure, but you can perversely play around with the arrangement of types within the network structure in interesting ways. So for example, here's a subset of the networks we used on the subjects that I call the minority power experiments for reasons that will become clear in a second. What I'm showing you here are 3 different networks just in 2 different layouts. Okay, so this is the exact same network as on the left. It's just that here I'm showing you a layout that separates the players that prefer red, that's indicated by the red vertices, from the players that prefer blue. And here I'm doing this traditional layout where you basically try to put the higher degree vertices in the middle and the lower degree vertices on the edge, just so you can see what's going on. Okay? But this is typical, okay? This is a network of 36 vertices generated according to this model called preferential attachment, which generates a heavy tail degree distribution, meaning that there will be a small but reliable fraction of the vertices with a number of neighbors that's much, much larger than the average. And what we're doing in these experiments is picking a small subset of the vertices to have a higher payoff for red, and the vast majority of them, in this case 30, to have a preference for blue. Okay? So all the vertices colored blue here have a higher payoff for blue, and the red ones have a higher payoff for red. Okay? So again, to use some lightweight economics language, the max social welfare solution here, of course, is that we all converge to blue. One type or the other has to acquiesce. It's better if the reds acquiesce, because then 30 players get their highest payoff rather than only 6 getting their highest payoff. Okay? The twist is that we haven't chosen the 6 minority red preferring players arbitrarily. We've deliberately chosen them to be the vertices with the most neighbors, with the highest degree. Okay? So what we're asking here, it's a laboratory test of the question whether a small but well-connected minority can systematically impose their preference against the greater good of the majority. Okay? The answer to this question, for better or worse, is an overwhelming yes. So without going into too much detail, the overall success rate in the 81 experiments we ran on this particular session, which included not just these minority power experiments, but a bunch of other networks that I'm not discussing here, it was basically well over 50%. It was 55 out of the 81 experiments ended in unanimity to one color or the other. So in 55 out of 81 of the experiments, everybody got paid something. In the remainder, everybody got nothing. Okay? But if you look at the subset of the experiments where we did minority power experiments, the success rate was much higher. Of the 27 minority power experiments we ran, 24 of them reached unanimity in the time allowed, which is much higher than the background rate. And furthermore, in every single one of those, all 24 of them, the convergence was to the minority preference. Okay? And people have different reactions to this result. Some people think, well, didn't we really already know this? But you have to remember, the well-connected minority doesn't know they're a well-connected minority. And in fact, if you look at the data, very often they'll acquiesce, because what happens in these experiments, of course, is that in the first milliseconds after the experiment starts, everybody initially selects their color with a higher payoff. In fact, these students are so competitive that the system that we gave them, what it typically does is it'll before the system becomes active and they can actually do anything, they'll see an initial view of their interface where they'll basically see what type they are, whether they have a higher payoff for red or blue. They'll see what their initial network structure looks like, and that'll be frozen there for them to just digest it for 5 seconds or so. But they can't the system's not active yet. It's not accepting any input. And in those 5 seconds, if you were in the room during the experiment, you would hear this low roar of furious mouse clicks, so that when the system became live, in the first milliseconds, their color would be registered on the logic that maybe this would influence the outcome, which, who knows, maybe it does. But, what I'm showing you here at the bottom are actual screenshots of the progression of one of these experiments. So this is the initial state where indeed everybody has chosen their preferred color at the beginning. And, if you're one of these reds, because you're well connected, you immediately see that you're vastly in the minority because you have a very good sample average of the rest of the network, right? So you see that you're surrounded by blue, and a natural thing might be to acquiesce. So you can see that here, in fact, is a member of the minority who's acquiesced a little bit later. And there are many, in every game there are instances of this. Yet somehow it always ends up being the case that eventually the dynamics work around to everybody choosing red. Okay? Okay. So let me just try to wrap things up. So we ran experiments like these for a good 5 or 6 years, and then we've been going in a couple of new directions recently that I'll just mention briefly in a slide or so. But in terms of the initial types of experiments I've been describing, maybe the most important takeaway message is that at least at this population size, human subjects are remarkably good across a diverse set of tasks, across a diverse set of topologies. The way you can quantify this is, right, we as the experimenters chose all the networks and we chose all of the incentives, all of the payoffs. So we can offline, we can compute 2 numbers. We can, for every network, we can compute the max welfare solution. In other words, we can compute what configuration of play by the subjects would have cost us the most in payouts to the subjects on that particular network and the particular incentives we gave them. So we can add up all of those numbers across all of the networks and different tasks we did over 6 years of experimental sessions and put that number in the denominator, okay? And then in the numerator, we can input the empirical analog, the total amount they actually got in all the experiments. So this allows us to make a comparison via payoffs of how efficient, how good subjects are on this. And that answer is basically 90%. So across all of the different tasks and networks we've thrown at the subjects, they've left only about 10% of the possible earnings on the table. Okay? network structure matters, as does the interaction with task. I already mentioned that. I didn't talk about it here, but one can, of course, do all kinds of analyses, not just at the collective level, but at the individual level, and ask, for instance, whether there are traces of, actual different styles of play or personality. So, for instance, in biased voting, I can define a measure like stubbornness. Let me define you to be stubborn. Any moment in the experiment that you're selecting your higher payoff color, despite a majority of your neighbors selecting your lower payoff color, okay? Because you're apparently holding out for your higher color. So I can sum up this stubbornness measure at the subject level and sort of look at the distribution of stubbornness across the subject population and ask whether it's greater than you would expect by chance, let's say by the random assignment of subjects to positions in the network. The answer to that particular question is yes. And then, of course, you can ask the next obvious question, which is, given that there's more than background variability in this particular characteristic, does it correlate strongly with wealth? Does being more stubborn statistically give subjects a higher payoff? The answer to that particular question is no, but for others it's yes. Let me just close by saying sort of two recent directions that we've been taking, one which is sort of a rather wild step, and the other is kind of a more traditional step. So there are many artificialities about these experiments that have bothered me over the years, but if I had to single out one, it was the fact that the choice of the network was exogenous to the experiment itself, right? So if we really think about this as the bare beginnings of some sort of theory about collective behavior in networks, and we think about, well, how would this apply to the real world? What we're doing here is extremely artificial, right? Because networks you would generally expect to form in response to whatever their purpose is. So, and of course, the management consulting literature is full of stories where, McKinsey goes in and is asked to study the organization of some large corporation, and their report 6 months later is like, well, the org chart you gave me on day one, that's complete garbage. Let me show you the actual network of the way your people interact with each other. And of course, there's always the story about some low-level employee who actually plays some crucial synthesizing role in these large organizations. So we have a lot of just so stories like these, but in all of them, kind of the story is that the network structure evolves in response to the task and is optimized for the task somehow. And in that sense, what we're doing here is extremely artificial. We've made one foray into this, which was quite thought-provoking. It was the first highly negative result I've seen in this line of experiments. We basically gave them biased voting experiments in which they had, at the same time that they were trying to solve this biased voting problem, they were also building the network at the same time. Okay, so I won't go into detail, but it was basically like a network formation game where initially nobody's connected to anyone else, so there's no way we're going to solve this unanimity consensus problem. And everybody at their option can choose to purchase edges to other vertices in the network at a cost that will be deducted from any eventual earnings, right? So collectively, we have to buy enough edges so that we have, some bare communication across the network so we can solve this coordination problem. But of course, I would greatly prefer that the rest of you purchase those edges that provide that connectivity so that they're not deducted from my payoff. Okay, so this was by far and away the most challenging game we gave to the subjects or for us to design the interface for, because now the network structure and layout is changing dynamically during the game and we have to render that. But the bottom line is that surprisingly the subjects did very, very poorly at this. And they really seem to, there's many reasons they might do poorly. For instance, there could just be information overload, just that trying to do these two tasks at the same time, trying to solve this unanimity problem while actually building the network over which you're solving it. Maybe it was just too much. But long story short, it really seems that the main way that they failed was by building networks that were actually poor for the task in question. And what I mean by that is that if you take the networks that the subjects actually built and then give them to a second set of subjects as a fixed, exogenously chosen network in which all they have to do is solve the biased voting problem, they don't have this information overload problem anymore, they do terribly, okay? So somehow the networks that the subjects built in service of the problem are bad networks for the problem itself, which somehow runs counter to this management consulting and org behavior literature, but it's early days. Okay. So let me stop there. The last thing that we're very recently doing, and this really I'm just talking about in the last couple of months or so, and one methodological thing that we're changing here is trying to move from a laboratory environment to running behavioral experiments on Amazon's Mechanical Turk, which many of you may be familiar with, which is a whole other methodological ball of wax with many, many complexities, even though in principle greater scale could be reached there. I think one next frontier in this line of research is to go from games in a network to games over a network. So by games in a network, I mean in all these experiments we had a large number of subjects performing their piece, a very simple task locally, even though the collective behavior might be complicated. But the subjects were kind of in the network. They didn't have a bird's eye view, and they didn't have to reason anything about other than their little piece of the problem in their local network neighborhood. I have the theory that all of this popularization about network science and the fact that you can now pick up the New York Times and read articles about what is the current diameter of Facebook, and people through books like The Tipping Point know about notions like hubs and connectors. We're much more as a society, it's not just that we're participating in more and more networks, which is also true, but I think there's more individual awareness of things like network structure and how it might influence collective behavior, and how your position in the network, might influence your outcome. There's much more of this kind of global or macro sense that I think even civilians have about networks these days. And so one of the things we want to do is to sort of return to single subject experiments in which we give subjects a bird's eye view of a network and ask them to solve some challenging cognitive problem, like the so-called viral marketing problem, where I give you a network structure and I tell you, okay, you can infect 3 of the vertices in this network, and there's some stochastic process which will then cause a cascade of subsequent infections. Which vertices should you pick? Which Facebook users should Apple give away, let's say, 1,000 iPads to, in order to maximize the grassroots spread of the next version of the iPad? This is, again, a hard combinatorial optimization problem that's intractable in the computer science sense, and we've sort of started trying to investigate whether subjects can actually do that, again, on sort of very small networks. And I'll stop with this slide that I won't explain. It's basically saying, that's basically showing that people do reasonably well at this task, at least in the sense of doing something much more intelligent than sort of selecting random vertices to infect. And more interestingly, they often seem to be, their behavior seems to often be highly aligned with pretty simple, greedy heuristics that do things like pick the vertices of highest degree, or even do that iteratively, like pick the vertex with the highest degree, but then remove its neighbors as sort of already being covered by selecting that vertex, and then among the remaining vertices pick again the one with highest degree, sort of a greedy method, but not a blind greedy method. Okay, let me stop there, and I guess we can take questions possibly over drinks. Thanks again.